So last time we are doing something in the middle of it. So let me share with you the class notes from our class last or just past Monday, right? So on Monday we worked with the so on Monday we worked with the level 2 analysis, right? We look at a hand car wash process, and then we calculate the capacity, and then we calculate the flow rate, right? All of these are easy calculation. It's just you have to understand the concept correctly by the correct answer, right? And then we calculate the utilization, the implied utilization, right? So those are the important metrics that a manager will have to know so that they can make the decision correctly. So after we do the calculation, we can draw the utilization profile to see what is going on, to visualize what is going on with our process, right? And then we would make our decisions accordingly. And then to improve efficiency, right? Regarding the implied utilization profile, we look at the numbers so that we can manage our capacity, right? So utilization and implied utilization are deep metrics inside the process for us as a managers to make the decisions on. All right, and after that, we move on to some new concepts. So the first time is a lead time, right? With the lead time, then we know that the lead time is just another name to call the flow time. And the flow time by the Little's law is I divided by R. We separate them, and that's why we have the lead time equals to the inventory times the cycle time, right? So I hope now you appreciate this equation. If we have a lot of inventory, and if we have the same cycle time, then the lead time will be more, right? So if during the holiday season, the Christmas season at Amazon.com, if they still have the same cycle time, but now there are so many orders inside the system, right? A lot more inventory, then the lead time will be much longer. So in the last week before Christmas in 2020, okay, they said that they could not honor the 2-day shipment, right? Because there is so much inventory inside the system. So you multiply with much more inventory with the same cycle time, then the lead time or the flow time for your order will be much longer, right? So it's going to be 2 days. And if you look around, there are many things like this. As long as you see more inventory, then the wait time will be longer, right? If you call a service center, the bank, if you call your bank, they might say that you have to wait for this much of time because in front of you there are other callers, right? Waiting in a line to talk to you. Oh, I did not share my screen yet. I'm sorry. I totally forgot it. Okay. So what I just talked about earlier is I went through the class notes last time, right? Last time we talked about the level 2 analysis. We went through a lot of calculation here, but they are easy, right? The more important thing here is the concept rather than the calculation. And then we try to visualize the process by the utilization profile, the implied utilization profile, right? And then by looking at the numbers, right, we make our decisions accordingly. And then the lead time, we just talk about the lead time as the inventory times the cycle time. So given the same cycle time, if the inventory goes up, then we will have longer lead time, which means that we have to wait for longer to receive our orders, right? So that's happened during the holiday seasons, or if you call the service center during the busy time of the day, then your wait time will be longer because in front of your call, there are other customers, right? So it's gonna take longer for us to talk to the associate. So that's the what we went over last time. Right? So today we just continue this some more concept by just one more concept, okay? The lead time, and I will talk about another concept, and then we move on to the next big topic, level 3 analysis. All right, so let me go back to the note. So we are still in module 4 about process analysis. And we are in the big topic of some more concepts. So last time we talked about the level 2 analysis, and then we talk about some more concepts, right? So we already went over the concept of the lead time. That's the L. From time to time, we're gonna go back to this lead time concept, okay? And then today we talk about the next concept called the required production time. Okay. Or T of Q. So if, for example, the customer order Q unit, we as a manager, we have to calculate how long it takes to produce Q units through, okay? To be a little bit more specific, for example, if you are the manager at a Pizza Hut store restaurant, then somebody has a birthday party on that day, they call in to order 20 pizzas, right? So as a manager now, you see that there's an order of 20 pizzas. You will need to calculate how long it takes to cook the 20 pizzas, right? If the customer wants the pizza by noon, then you have to start the cooking process at the right time, so that by noon you have the pizza ready to deliver or to give to the customers, right? You don't want to start it too early during the day. If you start the 20 pizza very early in the morning, then by noon the pizza will get cold, and then they are not as good as they should be, right? The customer will not buy from you again. So we have to calculate the required production time so that we can start the process at the right time, and that's happened in real life, right? That should happen every time in real life. So if we have the order like that, then the calculation will be the following. We need to differentiate between the two scenarios. In the first scenarios, the process starts empty. So if the process starts empty, then the required production time is calculated as the following. T of Q equals time through an empty system. It's a long phrase. I will explain what it is. I believe you already read it in Connect, right? If you're not clear, then this is a good chance for us to review it. So time through an empty system plus Q minus 1 times with the cycle time. So what does the whole equation mean? It looks long at this point, right? Let me draw a picture, and hopefully the picture will help us to understand what we are doing here. So our process is like this. Like this. We cook the pizza through. And when we talk about starting empty, then normally we talk about the early of the day, right? We opens up our business at 8 a.m. and then we start receiving the orders coming in. So at that time, we do not have any inventory inside the system. So for example, we think that we should start it early. Then here are the pizza. They are not in the process yet, but we imagine that there's a line of 20 pizza waiting to enter the process, right? Just some kind of, it's just based on our order. We know that there are 20 pizza are about to come in the process. So our calculation is the following. How long does it take these 20 pizza to go through the whole system, right? How long does it take for the last pizza to reach the end of the process? That's the time, the required production time, right, of the 20 pizza. So to do that, then we look at the first pizza right here. We need to calculate how long it takes for the first pizza to start the process and then end and exit the process, right? So that's why we have the first term right here, time through an empty system. That's the time for the first pizza to go through the whole process, where in front of it there's no other units, right? So we call it as time through an empty system. That's the time for the first unit to go through. And for the remaining units, pizza number 2, pizza number 3, all the way to pizza 20th, right? How long it takes us to cook this 19 pizza? Then we multiply 19. I hope you see why we have Q minus 1, because the one here is the first unit. We already take care of it. Now we talk about the remaining 19 units, right? So 19 pizza multiplied with the cycle time per pizza, right? Then we're gonna have the total time to cook 20 pizza through. To really understand the second term here, let me ask you a question, okay? So just imagine that there's a line of 20 pizza right here, right? When the first pizza reaches the end of the process, where would the second pizza be? Please feel free to share your thought in the chat window. Okay, so we have a line of pizza right here, okay? If the first pizza reaches the end of the process, then where would the second pizza be? Please feel free to share your thought in the chat window. By the way, I draw the line of pizza here, meaning that there's a distance between them, the cycle time. The cycle time will be here. Right, the time gap between them will be, okay, so many of you would say it is in the, some of you say in the start, at the start of the process, some of you say middle of the process, right? Okay, let me scroll up, okay. Okay, so here's the thing. So if you look at this line, this line is got a string of beats connected together, right? So if the first pizza come in here, then the second pizza will come in, the third pizza will come in, but they keep the same cycle time distance between themselves. So if the first pizza is here, then the second pizza will be somewhere here, right? They keep that distance. That's why we call it as a cycle time. On average, how long it takes for the next unit to replace the previous unit, right? So and then the first pizza continue to go more and more deeper inside the system, right? Yeah, Christopher, yes, I see. I hope now everybody see that. So when the first pizza reached the end of the process, then just imagine the second pizza is right behind it, right? Because it is a line of pizza that goes in at the same time. They are just going through, gradually going through the process. If you go to Chipotle, if you see how they, if you see how they bake the pizza, right? They put that on a line like this, and the pizza are going gradually through the oven, things like that, right? All right, so when the first pizza reaches the end, then the second will be here. Okay. So after one cycle time, what happened is the second pizza will exit the process. And where is the third pizza? The third pizza will replace the second pizza to be right here. So another cycle time, the third pizza will come out. Another cycle time, the fourth pizza will come out. Another cycle time, another pizza will come out. Right. So that's why for the remaining 19 pizza, we don't have to calculate time through an empty system anymore, because they already line up right behind the first one, right? So that's why after every cycle time, another pizza will come out, another cycle time, another pizza will come out. So for the remaining 19 pizza, we just count how many cycle times it takes for the 19 pizza to come out, right? So just 19 times, 19 times with the cycle time, then we have the time to cook the remaining 19 pizza. So in total, right, it is time for the first pizza to go through the empty system, and then plus 19 of the cycle times. Then that's the time to cook 20 pizza. I hope this picture helps to understand this equation. Otherwise, it looks very abstract at first, right? It's not that kind of intuitive to understand what that equation is about. So at this point, I would like to make a note here about the time through an empty system, how to calculate it. Then in that case, you have to look at the structure of the process, okay? Time through an empty system. To determine it, you have to look at the structure of the process. So this number depends on the process structure. All right, you just calculate how long it goes through the first section, how long go through the second section, the third, and then add everything up, right? Then we have the time through an empty system. So this is a side note here. I will have someone side note down here. All right, so that's the first scenario, how to calculate the time to produce the Q units if the process starts empty. In the second scenario, we calculate how long it takes to produce Q units if the process already has some inventory in it. So for example, if it is in the middle of the day, then we already have some pizza inside the process, so we already have it, and then here is the equation, right? The time to produce Q units equals Q units times with the cycle time per unit. And one more time, just draw the picture, and then we're going to see it. So we have the same process right here, right? It just, we start the batch at another time. It is in the middle of the day. So at that time, we already have the pizza inside the process already, right? One pizza is about to come out. Before that pizza, we have another pizza right here, another pizza here. And then we have other pizza about to come in, on and on, right? Then definitely this situation is different from the previous one. Now, every cycle time, one pizza will come out. Every cycle time, the whole line will move up by one position, right? This second pizza here will be at that position. The third one will come here. The fourth one will come here. So every cycle time, one pizza will come out. Another cycle time, another pizza will come out. So in this case, we have 20 pizza. After 20 cycle times, all 20 pizza will exit the process. And then we have all of the pizza ready for serving or for delivery, right? So that's why the equation is different, a little bit different from the first scenario. Okay, so you might ask yourself, right, what is the cycle time? And then remember, the cycle time is calculated as 1 divided by the flow rate, right? If we know the flow rate, then we can flip it to have the cycle time. And then and the tones of the flow rate itself, to calculate it, remember it is a minimum among the input rate, process capacity, and the demand rate, right? So in this case, what we do first is we determine the process capacity. And then look at the input rate, look at the demand rate to determine the flow rate. After we have the flow rate, we flip it to have the cycle time. So depending on number 1 or number 2, right? If for number 1, we have to calculate the time to an empty system, and then we take that cycle time, we put it here, then we have that required production time. In the second scenario, we just put it straight here, right? Multiply with the number of units, and then we have the required production time. So I hope, right, the picture tells us the difference between the two scenarios and why we have those equations. Any question for me regarding this topic? I hope you are good. Any questions are welcome. Right. So this is just some more concept. Actually, there are only 2 more concepts, right? The lead time and the required production time. They are not big models, so that's why I call that as some more concepts. So now we are ready to go through the last level of analysis. We call it as a level 3 analysis. Let me show you the example that we need to work on right now for this. That will be our module 4 and slide 44. Okay, so consider a process of 5 resources that are operated 8 hours per day, right? So our process has 5 resources, and it is open for 8 hours per day. In the slide, there's no specific context here, right? I would like to call these whole thing as a restaurant process. So let's consider a restaurant with 5 resources, and the restaurant is open for 8 hours per day. The restaurant works on 3 different products, A, B, and C, right? So this there are 3 types of dishes that the restaurant serves. Demand for the 3 products is 48 units per day, 50 Bs per day, 60 Cs per day. So these are the demand per day that the question gives us, right? So in this case, right, we talk about the level 3 analysis because we talk about multiple products, A, B, and C, and at the same time, we talk about 5 different stations, 5 different equipments, 5 different resources or steps, right, for the dishes to go through. So that's why here they give us this matrix, this table. They tell us how long it takes to process 1 unit of A through station 1 and 2 and 3, how long it takes to process B through each of the stations, right? So it is more complicated than before. In level 1 analysis, we only have 1 step, 1 flow unit type. In level 2, we have, even though we only have 1 flow unit type, but then we have multiple steps, right? But here in level 3, we, beside the multiple steps that we have to deal with, now we have to deal with multiple units, right? Unit types. So that's the complexity of the process that we have to deal with. There are 2 things that we have to do here, 2 big things. Number one is we draw the process flow diagram to make sense of it, to visualize it, right? And the second is we would carry out our process analysis. What we are doing next is very similar to question 24 in your homework and also the part 3 of the project. Okay, so I hope that what we do here will help you, will benefit you when you work on other items at home. Okay, so let's start the detailed work here. Okay, so we are still in module 4, right? And we move on to a big topic. That's level 3 analysis. In this level 3 analysis, we are looking at processes with multiple steps. And at the same time, we have multiple low unit types. Or apt UTs. And our example is, let's call this as a restaurant example. This is module 4 and on slide 44. Right. So what we are doing next is very similar to what you do for question 24. But then let's write out the information here first. So we have 3 different products. And that's why in this case we have 3 different flow unit types. Right? They are A, B, and C. For the ease of our discussion, we would call the A here as an ice cream. B as a burgers. And C as the fries. The French fry. Okay. If right now, if you stand up and if you grab some food to eat, then of course you are free to do that, right? That's the advantage of doing things online. Everybody has a freedom of eating anything during the class time. Okay, but okay. So again, we call these as an example, the loose example, so that we can make more sense of our calculation. So this is a restaurant. They are serving ice cream, burgers, and fries like McDonald's, right? And they tell us that the demand per day is the following. So demand of A is going to be 40 ice creams, right? Demand of B. So it means that in one day the customers order 40 ice creams, and then they order 50 burgers. They order 60 fries. So when we have to deal with 3 different products like this, potentially the calculation would be very hard. But in our class, we try to simplify it so that we can handle this effectively. To make it simple, okay? So that's why we need to make the following assumption. We assume that we have a fixed product mix. What does that mean? It means the following. So the proportions of the demands are fixed among the 3 products, okay? So for 40 ice creams that we sell, we're gonna sell 50 burgers. We're gonna sell 60 fries. and these proportions are assumed to be fixed. We assume it is fixed so that we can effectively go through the calculation. Or we can simplify these, and we say that for every 4 ice creams, we would sell 5 burgers, and then we sell 6 fries, right? And remember, we assume that these proportions are fixed. The proportion do not change over time. No matter what we do, the proportions stay the same. So that's the first thing that we need to choose, right? We choose it to be simple enough so that we can work on the analysis. And then another thing that we have to make the decision on is the following. Now we have to deal with 3 different products. At some point in time later, we have to add things up. Then we cannot add the ice cream with the burgers and the fries together because they are totally three different things, right? So we cannot, conceptually, we cannot add 3 different things of 3 different natures together, right? So we have to find a common unit among them so that we can add things up. So in that case, we're gonna choose the common unit, common flow unit of or as a minute of work. Okay, because all the food, whatever they are, they take time to be cooked, right? So it takes time to prepare the ice cream. It takes time to cook the burgers. It takes time to cook the fries. So the time to work on them, right, is a common among all of the 3 units. This is for question 24. Last time we worked on the level 2 analysis. That's for question 23. Today we work on the 24 actually, right? Okay, so you're welcome, Matthew. So in this case, we talk about minutes of work as a common unit among the ice cream, the burgers, and the fries. And here is the thing. The question asks us to do the process, to draw the process flow diagram so that we can make more sense of it, right? So let me draw the process flow diagram with you first. So that we can kind of visualize the process. So here is the process flow diagram. So this is a restaurant process. It is a cooking process. The customer has to order first, and then we start cook things, right? So the start point of the process is the products are ordered. So after the customer order, then product A will flow in the process. Product B will enter the process. Product C also enter the process, right? So that's a starting point of the process. And now next, what we do is we look at the processing time in the table. If we look at the processing time, right, it takes, I'm just looking at the slide 44 right now. So the processing time for A is 5 minutes at station number 1. It just says the following. It takes 5 minutes to prepare the ice cream at station number 1. But that 5 minutes also just says the following. The ice cream has to go through station number 1. Right? That's the nature of the process and the product. The ice cream would have to go through station number 1. Just one more time, when we talk about the ice cream, the burgers, the fries, they are just kind of loose names so that we can kind of make more sense of what we do. So product A's would have to go through station number 1. Right, so this is resource 1. Actually, all A, B, and C would need to go through resource number 1. So we have all the 3 arrows here. And then if we look at the station number 2, the 3 products also have to go through station 2 because we have the processing time for A, B, and C, right? So we would draw the station 2 like the following. Right, so A has to go through it, and then B, and then C. In our process, right, sometimes there's a wait time, transit time, or buffer time. So all of those will be denoted by the triangle. So in this case, I would draw the small triangle here. Right, so after the customer order, it takes some time to relay the information to the kitchen, and then the kitchen will start cooking the items, right? And between the stations inside the cooking process, there might be some wait time. They are done with it, and now they have to put the item out to wait for the next step, right? So that's a wait time. And all the wait time will be denoted by the triangles. Okay, so that's happened at station 2. At station 3, only A goes through station 3. Because at station 3, if you look at the table on slide 44, B and C will have 0 processing time. 0 processing time just means that B and C skip resource number 3. So how to draw it here? I use my creative drawing to draw this part of the process, okay? So we have resource number 3, and we have the A goes through it, right? But because B and C do not go through it, so that's why I draw that R3 to be that short. And now we have the resource number 4, right? So B goes through that 4, C goes to that 4, B here, C here, right? There might be some wait time right here and right here. That's okay. That's the nature of the cooking process, right? And then they all go through resource 5. You know what? There's a disruption outside. Please bear with me. I need to walk out for 1 minute, and then I'll come back. Okay. Thank you very much for the wait. I need to deal with something, and I'll be right back. Okay, so sorry for the disruption. I'm just back. Okay, so I will talk about that, Matthew. I will explain why B and C would not go to 3, right? For now, we just take it for granted that by the nature of the process and the product, B and C do not go to 3. Only A goes through it, right? Let's draw let's finish the diagram, and then I will explain it. So A, by the nature of the product A, it will not go through resource 4. So we just bypass resource 4 like this. So we have R4 right here, right? And if you look at the chart one more time, then all units, I mean, all products will go through resource number 5. So at 5, here is what happens. I draw that R5, resource 5 right here. And then A goes through it, B goes through it, C goes through it, right? All units will go, all products will go through resource 5. There might be some wait time along the way. And finally, when all the dishes are ready, right, then they will be served to the customer. So the end of the process is the food is served. So we have products A, products B, products C. Right. It might be some more wait time here. even though the food is already ready, but then the server is busy with another table, right? So that's why it takes some more time for the server to deliver the food to the next table. So all the little triangles are for the wait time. Okay, so now what happens? Why do we have the skipping? Why do we have all of the skips here? Right. I would like to answer that when I draw the table with you, and then we will see why there are some skips here. So we are done with the process flow diagram, and now after that we work on a very long table. So with a lot of calculation in it. You know what? I already help you by giving you the Excel, the table template in the question. In question 24, I actually give you the table. The table is actually the sequence of steps that we have to go through, right? You just work on the table row by row, line by line, and then you're going to finish the whole thing, okay? So please understand that I already help you with the steps here in the question. So let me show you how to go through the table. And then I will explain why do we have to skip. Okay, so we draw a table like this. We lay out the steps horizontally. So we have resource 1 right here, resource 2, resource 3, resource 4, and then resource 5, right? In the book, normally they lay out the resources vertically, but I prefer to do it horizontally because we would like to reserve the first column for very long names, long variable names. So the first line that we have here is the number of workers. They say that the question gives us that there are 2 workers at station 1, 2 workers at 2, 1 worker at 3, 1 worker at 4, and 2 workers at 5. So for now, we take these as granted, right? As a manager, you wouldn't make the decision on this. You can change this. But for now, we just analyze what is happening with the restaurant, right? And we don't change anything yet. We just take these for granted. Okay? And then they tell us the processing time. So processing time for the ice cream, right? So in terms of how many minutes per ice cream unit, and then per worker. You know what? I would like to make this shorter so that I can write the whole thing in one line. So we talk about the processing time of A in terms of how many minutes per ice cream unit per worker. Let me copy the information from the question. So it takes 5 minutes to process the ice cream through station number 1. Right? That number is given by the question, 5 minutes for ice cream. That's station 1. And then it takes 3 minutes to process the ice cream unit at the station 2. It takes 15 minutes by the nature of the product and the process. It takes 15 minutes to process A through station 3. Remember, the ice cream is just a loose example so that we can understand this more. And then at station 4, we have 0 minutes. So the 0 here doesn't mean that the ice cream takes 0 minutes to go through station 4. This 0 means that the ice cream will not go through station 4. For example, if station 4 is a fryer, then the ice cream will not go through the fryer, right? So that's why we have the skip. at 4 for the ice cream. And then at 5, we have 6 minutes. Right. So by the nature of the process and the product, sometimes we see that skip. And for that skip, we would write out the number 0. It means that product A doesn't go through station 4 at all, right? So in real life, you have to specifically look at the nature of the process, the nature of the products, to see if there are some skips in the process, right? Let me give you one quick example, and then hopefully you can appreciate when we consider that as a skip and when it doesn't skip. Okay. So earlier I say that an ice cream would not go through the fire, right? That's why we have that 0. But in real life, you know what? An ice cream might go through a fire. Okay, an ice cream going through a fire. Just imagine. Have you ever tasted the so-called fried ice cream? Has anybody here in our class tasted fried ice cream? Matthew, not yet. Okay. How about other students? Oh, Solin, we did. Okay. Not yet. Vienna, not yet. Okay. Ying. Oh, okay. Jose, no. Sophia. Oh, Sophia did some. Okay. Helen, no. Okay. Michael, not yet. Okay, so let me explain what it is, and you'll see why the ice cream goes through the fire. So here's how they do it. They scoop a scoop of ice cream. Okay, it's a bowl of ice cream like this, and then they dip the bowl in a pot of dough, raw dough. The raw dough is made of flour, different kind of things, right? For it to taste good, to have the good texture later on. So the raw dough is thick and sticky, right? So when you put the ice cream ball into it, then the dough will wrap around the ball, the ice cream ball. You pick the ice cream ball up and dip it in the very hot oil pot. So the hot oil will cook the dough instantly, right? The flour instantly. Yeah, I understand, Sophia. I myself tasted the fried ice cream when I was little when I was in Vietnam. Okay, Matthew, it's okay. Everybody has their own kind of thought about it. That's fine. You know what? So you have an ice cream ball, right? Very cold inside, but very hot outside. Of course, you want to wait for it to cool down a little bit, and then you taste it. From time to time, my students think that it is a cool thing to taste, and actually they already tasted it. So here is my hint for you. If you want to taste it here in California, then
What's the name of the ice cream?
fried ice cream.
Fried ice cream.
Yeah, but technically we fry the ice cream. You know what? You can find it at the LA Fair. Okay, so I don't think the LA Fair is open this year, but next year it should open, right? If you have a chance to visit the fair, then look for it. You might. Yeah, I see a note here. It's easy to make, but you need to be very careful. Okay, you don't want to drop the ice cream ball into the hot oil. The hot oil might splash. So in terms of the process, you have to come up with a very good way to do it. For example, you have a little cooking basket. You put the whole thing, the ice cream ball in the basket, put it in the dough first, make sure that the dough wrap well around that, and then you put that in the pot of oil, right? How to find this store? It's not a store. You go to the LA Fair. That's a Los Angeles kind of park, right? It's a seasonal fair. LA County Fair, yeah, Matthew. And then you might find it over there. I don't know. It depends, right? Next year they should open it. you might be able to find it. Oh, really? A lot of fried stuff. Okay. I tasted it long time ago. And here it's hard for me to find it. Okay, good. Yeah, so I hope you have a chance to try it, and then maybe you change your opinion, Matthew. Some students say that they love it. Okay, the outer layer is made of special texture. So inside the heat of the layer, right? They also have some kind of texture for you to taste. So you might like it. Okay, I like it. It's not super special, but it's good. It's crispy outside, so you taste the heat and the chill at the same time. That's what it is about. Okay. All right, but let's go back to our class. I give you that example to say that in real life you have to look at the specific process and products to see when the products skip and when they don't skip. Okay. You need to look at the specific methods. I mean, the process and the products. All right, so that's the first products. Now let's talk about the second product. B in terms of how many minutes per the burger per worker. Yeah, in the book they never say per worker, but just imagine we have to say per worker. Otherwise, it's arbitrary, right? So if one worker at worker station number one on the burgers, then that worker will have to spend 5 minutes on the burgers per each burger, right? And then 4 minutes per each burger. Two, the burgers will skip the number three. For example, if number three is an ice cream machine, then the burgers will skip the ice cream machine, right? Except if you come up with a recipe where you put the ice cream into the burger, okay? Then that's not a skip, but the common sense, right, is the burgers will skip the ice cream machine. And then at 4, we have 3 minutes. And then at 5, we have 6 minutes. All right, so that's the processing time. And that's why earlier when we draw the product B, right, we see that product B skips number 3. So by the nature of the process and the products, B skips resource 3. And then we talk about the processing time of C in terms of how many minutes per C per worker, right? So we talk about the fries now. The fries will take 5 minutes at station 1. Each one of them takes also 5 minutes at station 2. The fries will not go through the ice cream machine, so that's why we have that 0. That's skip, and then the fries will spend 3 minutes at station 4 and 6 minutes at station 5. So this is the first part of the table, okay? And we call these as the technology matrix. Technology matrix. Why is that technology? Because it tells us the processing time, how long it takes to cook the dishes through, right? If we have a better process, we have better equipment, we redesign the products, then we might cut down the time that you see here, right? You cut down the time, it takes shorter time for the dishes to go through the cooking process, right? Then we have better technology. So in a sense, right, we talk about technology right here with the processing time. The workers are different, right? But this part, the main part that we see here are the processing time. So that's our technology right there. Okay, so what do you have? The technology. Now, as a process, we can talk about the capacity or the supply, right, side of the process. And then later on, we can talk about the demand side of the process. Let me redraw this a little bit. Oops. So now let's talk about the capacity or the supply side of the process. So capacity, we would not talk about how many ice cream per day or burgers per day that can be produced, okay? In this case, we talk about minutes of work per day. But for now, we work on this per hour first to easily grasp the concept. So instead of how many ice cream that the worker can produce per day, we talk about how many minutes of work that the workers can offer, can render, can dedicate, and can supply per hour, right? So
Minutes per hour?
Oh yeah, per hour first. That's an intermediate step. We do the per hour first, so that later on we can scale it up to whatever it is during the day. Oh, it might sound like a tautology, right? How many minutes per hour? It's not that. Here we talk about how many minutes of work, not the clock minutes, okay? How many minutes of work that a worker can render in 1 hour. So we know that in 1 hour, if we do not have any break time at all, a worker will work for 60 minutes, right? But here we have two workers. So the two workers between them can offer, can supply, or can render 120 minutes of work, or sometimes we call it as they can offer 120 minutes of service to the cooking process, right? They can dedicate, they can contribute 120 minutes of work to the restaurant cooking process. So that's the meaning of this, right? We are not counting how many minutes in 1 hour. We talk about minutes of work in 1 hour here. So remember, earlier, that's why I make a note that we would choose the flow unit to be the minute of work, so that we can add things together. We cannot add ice cream with burgers with fries directly, but then if we can convert everything to the minutes of work, then we can add them together, right? So that's the capacity at station number 1. By the same token, we can do the capacity at station 2. So there are two workers, right? Each one of them works for 60 minutes in 1 hour. So 60 times 2, then we have 120 minutes. Maybe there's a process where they do not, they give the workers 5 minutes break time every hour. Then the minutes of work per hour would be 55, right? But here we assume that they work all the time. So we take 60 minutes times 2. Okay, so for resource number 3, it takes 15 minutes. I'm sorry, because there is only one worker, right? Then that worker can offer 60 minutes per hour. And then the same for 4, 60 times 1. And for 5, 60 times 2. So at station 3, because there's only one worker, that worker can only offer 60 minutes per hour. Minutes of work or minutes of service, right? 60 minutes per hour. For 4 and at 5, the two workers can offer a total of 120 minutes of work per hour, right? So we do this as the basis so that we can scale it up for the whole day. Because at the end of the day, they talk about how many ice cream per day, how many burgers per day, and the workday is 8 hours, right? So now we can scale it up for the whole day. So the next step is we calculate the capacity in terms of how many minutes of work per day. Right. So what we have here is the following. It's easy. It's not difficult at all. We know that there are 8 hours in one workday, right? So you would multiply 120 with 8 hours, right? Or here we do the same 120 with 8. Yeah, I see that. I see the answer from somebody, right? And then we have 60 times 8 here, 60 times 8 here, right? More and more. Oh, we are kind of behind, so I need to speed it up a little bit. And then we have 120 times 8, right? So here is what we have. We have 960 minutes of work, 960 minutes of work, 480 minutes of work here, 480 here again, and then 960 minutes of work here again, right? So this part of the table, we would call these as the supply matrix. How much time that each of the station can contribute to the restaurant's work, right? How much time they can dedicate to the products. So we call that the supply matrix. This is an internal supply only, right? Supply to the work inside the restaurant. So that's the second part of the table. We calculate the supply side of the restaurant. Then in the third part of the table, we work on the demand side, right? So here's the demand side. For you, you just extend the table. For me, I need to do the frames again so that we can know which station it is. So I write here station 1 here, 2, 3, 4, and 5, right? In real life, they are the salad station, the ice cream machine, the oven, the fryers, the boilers, right? The microwaves, a lot of them. But here we only consider 5. And then we have the first column for the names of the variables. Maybe it should be smart. Okay, so we have, first of all, we need to write out the demand. We have the demand for the ice cream, right? In terms of how many ice cream per day. But the notion here is the following. We know that there are 40 ice cream per day, right? So those 40 ice cream will require work out of station 1. So we write out number 40, with the meaning that those 40 ice cream require work out of station 1, demands work. That's why we call this as a demand side of the business, right? Those 40 ice cream demand time from the workers. And then at station 2, those 40 also require work out of 2. And again, those 40 ice cream require work out of 3. And those 40 ice cream do not require any work out of 4. Right? Remember, 4 is a fryer. So that's why the ice cream doesn't require any work out of, it doesn't go through the fryer, right? It doesn't require the worker station for the work on the ice cream at all. And then those 40 ice cream will require work out of 5. So the next one is the demand for B. So how many burgers per day, right? So remember, the question gave us that the customer ordered 50 burgers per day. How would we write out this line? Let me work on this with you. So those 50 burgers will require work out of station 1. 50 burgers require work out of 2. But then the resource 3 is the ice cream machine. And that's why the burgers will not require any work out of it. So conceptually speaking, we have to put that 0 here because no burgers require work out of station 3, right? And then those burgers will require work out of 4, and those burgers will demand time from the workers at 5, right? So that's the meaning of these numbers. Of course, we know that the orders per day is 50, but then we talk about how much demand is required, how much work is required out of each of the stations, right? So that's why sometimes we have the zeros. And the demand for C in terms of how many fries per day Here is 60, 60 again, right? And the fries will not go through the ice cream machine, so we have that 0, and then 60, and then 60. The larger the number, the more work that the workers will have to do. So the demand here is not the customer demand, okay? This is a demand of work out of the station. So that's the demand side. But at this point, right, we realize that we cannot add these three numbers together. If you add 40 with 50 with 60, you have 150. But then I would like to ask you, what is a unit of 150? Then nobody can say it clearly, right? So we cannot do that conceptually. We have to convert everything to the common unit before we can add them up. And here is a step to do the common unit. We would call this as a workload for the ice cream, right? Now we convert the ice cream into the minutes of work per day, not the physical units. Now we convert all the physical units into the time unit. So we know that if you look at the first the technology part of the table, right, we would know the processing time. So I look at the table right now. I know that, or you can see that it takes 5 minutes to process one ice cream through station 1. But because there are 40 units of ice cream, right? So we take 5 times 40 to have the number of minutes required at station 1 for the ice cream. And then the 2, I see that number 3 minutes per unit, but because we have 40 units, so we multiply that with that. The next one, we do that 15 times with 40, right? 15 minutes per ice cream, and then for the ice cream, we multiply them together. The next one is tricky. This one, to be correct, you have to multiply 0 with 0. So the first 0 is, it doesn't take any minute for the ice cream to go through 4. And then the second 0 says that no ice cream go through 4, right? So that's why we have that 0 times 0. And the next one is we take 6 minutes per ice cream times for the ice cream. Right, so we would have 200 over here, 120 here, 600 over here, 0, and then 240 over here. All right, it's not difficult at all. It's just a concept behind the numbers. At station 4, the ice cream totally skips the fryers. So no minutes at all per unit, and no units at all through that 4. That's why I had to have that 0 times 0. Yeah, minutes per day. That's correct. That's correct. So it means the following: the workers at station 1, no matter how many workers it is, will have to work for 200 minutes at station 1 so that they can process the ice cream through. Okay, so that's the meaning of the number. And then by the same token, we can do that workload for B in terms of how many minutes per day. Right, we only have 5 minutes, so I think we can do it. All right, so here's the thing. If we look at the table, right, if we look at the B row, it takes 5 minutes to process a burger through station number 1. So 5 minutes per burger, but then we have 50 burgers, right? So you multiply that 5 with 50. We scale it up by 50 burgers. And then by the same token, we're gonna have 4 minutes per burger, 2, you scale it up by 50. And then this number is 0 times 0 because the burgers will not go through the ice cream machine, right? So no minutes per unit, and then no units going through it, 0 times 0. In the table, it means that you multiply that 0 with the 0 earlier in the table, okay? I have to say this because in the part 3 of the project, you have to link the 2 cells together. You have to know which 0 times with which 0 in the table, right? To be correct. So that's 0 times 0. And then the next step is we do I'm looking at the table right now. It is 3 minutes per burger. We have 50 burgers, right? And then 6 minutes at 5 times 50 burgers. So one more time, the calculation itself is very easy. Here we have 250, then 200, then 0, then 150, and then 300 here, right? So for the burgers, this is how much the workers will have to work at the 5 station, right? How many minutes per day, of course. And then for C, the workload for C in terms of how many minutes per day, then you will need to do that as the following. Again, we look at the table. It takes 5 minutes to process the fries at station 1, and then because we have 60 units, right? So we multiply that 5 with that 60. Okay, if you can do it quickly, share with me what we will have for station 2. What number should I write here? All right, so Matthew already got the number. Yeah, so I look at the, that's correct, Matthew and Philip. Yeah, so it takes 5 minutes, and then because we have 60 units, right? We multiply that with that. The next one, we got 0 times 0, and then we have 3 times 60. That's why I believe now everybody sees that. Yeah, that's 180. And then we have 6 times 50. Okay. So in total, we have 300 here. And then also 300 here, 0, 180. And then, oh, I'm sorry, I got 50 here, but actually that's had to be 60, right? And then we got 360 here. Okay, so one more time, what do we do here? Let me recap very briefly, right? Okay, so here we talk about the physical demand. How many ice cream that the workers have to work on, how many burgers, how many fries that the workers have to spend time on. But then because we cannot add these numbers directly, right? That's why we do the intermediate step. We convert everything to the minutes of work. Minutes of work here, minutes of work here per day. So that at the end of the day, we can calculate the total workload, right? So at the end, we have the following total workload in terms of the minutes of work per day. So the workload here are all for 3 products, right? So the total will be the sum of the 3 numbers. So for example, at station number 1, please look at it. We have 200, 250, and 300. Yeah, I believe now you see the logic, right? Then the number here should be 750 minutes in total. The workers at station 1 will have to work for this many minutes in a day so that they can fulfill their orders, right? At the station number 2, if you add them up, we have 20 minutes, right? At station 3 is easy, 600 plus 0 plus another 0. And that's why we have 600 minutes over here. The fourth one will be 330 minutes of work. And finally, we have 900 minutes of work here, right? So in total, the workers will have to work for these minutes so that they can honor the order from the customers, right? Okay, so this is called the demand side. Next Monday, we work on comparing the demand with the supply to see if we have enough capacity to, per day for each station. So next Monday, we continue our example. I wish everybody a great weekend. Have a good rest of your day, and then I'll see you back next Monday. Okay. So thank you all for joining me.
Thank you.
Yeah, thank you. Thank you, everybody.